session. So our first speaker for this session is going to be Xuecheng Shao. He's from Pavanelos Group at Rutgers University. So welcome, Xuecheng.
Yeah, hello everyone. My name is Xuecheng Shao from Parallelization Research Group. It's my pleasure to give a talk today, and today I'm going to talk about some thoughts about a density functionalization of QM. So firstly, what's the quantum mechanic method? So limits to our research interests. So here I list 4 ab initio methods here. From the left to the right, the efficiency is increasing, but the accuracy is decreasing. And the first one is we directly solve the many-body problem, which is very difficult and time-consuming. We barely use it in the molecular dynamics. And the second one is one of the most widely used ab initio method, Xuecheng density function theory, which is still accurate enough, and we can apply to hundreds of atoms. But that's also the limitation because it's dependent on the orbitals, and the scaling is a cubic scaling. It's hardly to extend. And we directly go to the last one is opt-free density function theory, which is fastest density function theory. And because it's only based on the density, all the functional related to the density, no need for the wave function. So it's a linear scaling, can be approached to millions of atoms. We also did some like 100 million atoms with parallelization. So it's very fast. But it's less accurate than the Xuecheng DFT, and also limit on some metals and semiconductors. So what else we can use? So there is one method, Subsystem DFT, want to achieve the same accuracy as Xuecheng DFT, but still want to have the accuracy, actually the accuracy of the Xuecheng DFT and the efficiency of the opt-free DFT. So what's the Subsystem DFT? Subsystem DFT is adopt a divide and conquer to split the system into some smaller interacting system, and the total density is just the sum of each subsystem. And we can use Xuecheng DFT for each subsystem. And recently, we also developed a strategy that we can use opt-free DFT for one subsystem. And now the NG can be split into added term and non-added term. So added term just DFT NG for subsystem, and non-added term is just interaction NG. The interaction NG is given by non-additive, kinetic NG, non-additive exchange correlation, and electrostatic interaction NG between subsystems. All these functional terms is depend on the density, so it's a linear scaling, no problem. But the question is how to calculate kinetic NG, because we don't have exact kinetic energy density functional. So we don't know how to do it, but good news that we can use some opt-free kinetic energy density functional. And in sDFT, normally people use local or semi-local functionals. And our group also first time implementing local functionals in the sDFT, so which much improves the sDFT result. So how accurate is sDFT? We use commonly people use test size as 66, and we text interaction energy for different kinetic energy functional, including local, semi-local, and non-local. We also recently developed new semi-local functionals just for subsystem DFT. And from here, we can see that for these weakly interacting systems, sDFT can approach correctly and almost as accurate as non-local Xuecheng DFT. And even compare to some high-level quantum mechanical method like MP2 CSSD with our non-local functional or our new developed semi-local functional SMP, we are still good, and the results are totally acceptable. So during the developing of subsystem DFT, our group have two codes. The first one is EQE, which we based on the Kongshan code quantum expressor, which is written by the Flowchart language. We developed for many years, but recently we found that it's very hard to add some new features, and it's also very hard to update. So we just stopped developing, and we are moving to a new subsystem DFT code, eDFTpy, which is a fully Python. And we implement some parallelization scheme here, and we now can include op-free, Kongshan DFT, and op-free DFT part, we directly use our own DFTpy code, which also a Python code. It's already paralleled. And for the Kongshan DFT part, we still use quantum expressor, but because we are in the Python, we still want the data is passed in the memory. So we also develop a Python interface for the quantum expressor we call QEPy. Now through QEPy, you can easily to call quantum expressor from Python. You can get density, set potential, and you also can very easy to update functionals in the QE just through the Python side. It's very efficient and easy to use it. So all of these make our eDFTpy possible to run a real subsystem DFT. Now we're also collaborating with some other research group to adding some new drivers in the eDFTpy to support the different kind of subsystems. So this is a flow chart for subsystem DFT in eDFTpy. The first step, we initialize a global grid. We generate the global communicator. Then we build subsystem, initialize subsystem drivers, and each subsystem will have their own communicator to the parallel. And now for the subsystem, we have DFTpy, QE, and others like invariant cluster and MBX. All these drivers are being developed. We are still working on that. Then we evaluate embedding potential and get subsystem densities. But all these subsystems will be run simultaneously, so it's fully paralleled. Then we can update the density. If you want, you can yield the global density. Next, just check the convergence. If not, just repeat the process until converge. So in order to deal with a very large system, so in the eDFTpy, we use a totally different parallelization scheme compared to the conventional DFT. So in the eDFTpy, subsystems are assigned their own set of CPU and simulation cell. So the subsystem simulation cell can be much smaller than the global cell. And each subsystem will be run their own calculations separately. But the global potential, such as quantum potential, still need to be calculated on the global grid. So one of the most important things in the eDFTpy, we completely avoid getting the global data. So there is no I/O node to save the global data. So in principle, there is no limit to the system size as long as you have enough CPU and there is no big subsystem in there. So you can get as big as you want. So how about the speed? Because we want to use subsystem DFT because it should be very fast than the Kongshan DFT. So here is an example. We study a condensed phase carbon dioxide with Kongshan DFT code, quantum expressor, and two subsystem DFT code, EQE and eDFTpy. And we can see that the subsystem DFT code scale linearly. And people always say that Python code is much slower than the Flowchart code. So that's why people don't want to move to the Python side. So here is an example that we still use Python. but we are parallel also. And the results show that our Python version of the subsystem DFT is as good as Fortran version of the subsystem DFT code. So we can easy to use it, and also the speed is good enough. So what else subsystem DFT can do besides the normally geometry relaxation, molecular dynamic? So one of those things that we said subsystem DFT works very well for the weakly interaction system, but when the subsystem interact very strongly, the subsystem DFT won't work well. But now we can merge the strongly interact system to one system and run the simulation. If they are weakly, we can split again. So we develop a adaptive subsystem DFT and to make the simulation. With adaptive subsystem DFT, we are studying some metal hydrogens. If there is also a big metal system in the system, so that's big metal subsystem, we also can use optrade DFT. So we can use optrade DFT with Xuecheng DFT to run the subsystem DFT. And we also can run some TD-DFT subsystem DFT calculation. Yeah, so we are talking about QMM, but why we talk about so much about system DFT? Because I think most of this technique and method can be used for the QMM also. So this is a general way, traditional way people thinking about QMM. So there is one pieces people are more interested, use QM method to describe. And this QM system is surrounded by the environment we call it MM system. Now the total energy is QM energy plus M energy and the interaction energy. But we are doing subsystem DFT. So when we look at the QMM, we are thinking it should be like this. This is the general way of the QMM, because the left one is just a case of the right one. And in this general way, there can be many QMM systems and also many MM subsystems. So all these QMM subsystems can be one MM system, and all these QMM systems also can be one QMM system or different subsystems. If we replace the QM system with MM system or MM system with QMM system, it will be just like a standard subsystem DFT. So when we look at the total energy of subsystem DFT, it's very similar to the QMM energy. The only difference is in the sDFT, we use density-functional to evaluate interaction energy. If we can get density for the MM system, we can use the same functional and same technique in the sDFT to run this QMM simulation. So the key question is how to get MM density. So here, example that we are using, we don't have MM density, but generally they have a point charge and point depots in the MM system. So for the point charge, we can give a pseudo potential, which is a local pseudo potential. And for the density, we can generate based on using a Gaussian function with a smooth, and the scale is the number of valence electrons minus the charge. And for the point dipole similarity, we can use derivative of the dipole dot product to the, we can use derivative of Gaussian function dot product of the dipole. And now we build this pseudo density for the MM system, and this pseudo density just including the point charge pseudo density plus the dipole pseudo density. Now, the total density of the system is the sum of QM density and MM density. Even MM density is a pseudo density, and the interaction energy can be two parts. One is electrostatic interaction and non-additive term. Interaction energy including external term, heart rate, and water energy, and non-additive term including non-additive kinetic energy, non-additive exchange correlation. People may be worried about that if we use a density functional run the calculation, it must be very slow and cannot apply to very big system. But all this functional is just dependent on the density, so they are linear scaling. Here are some examples we did with Opt3 DFT. So we run a fully density optimization for the bulk system and the nanoparticle. Even with one CPU, we can easily run million items of bulk system and just 100,000 items for the nanoparticles. As soon as you have enough memory, even you can run this calculation on your laptop. So it's fast enough and linear scaling. So we can implement the QM method as a standard sDFT method. So the flowchart is the same when we do this QM method. So only different is when we use MM, we need to use a different embedding potential because they are still not the real QM system. And the subsystem density also will be different. So more specifically, first we need to evaluate the total potential and the QM electrostatic potential on the global grid. And the QM subsystem will receive the total potential and evaluate the embedding potential. So the Hamiltonian equation gets a new density. Here can be not only one subsystem we call QM. Actually, you can put many QM, just use regular subsystem DFT here and put many QM subsystems. On the MM side, it's received just a QM electrostatic potential and evaluate new dipole, build a new pseudo density, and we can update the density for the global density, run another calculation, repeat the process again. So it can be fully self-consistent, get the density, and we can even to see the total density for the global cell, or we just can look at the density for the QM size. So here is a preliminary result. We start the intermolecular interaction for the water diameter. The left one we use as a MM system, we use MBX code. On the right side, we use QM system and with QE software. All this calculation, we just use the sDFT way, we implement it on the eDFTpy code. So the MM model is parameterized on the PB, Xuecheng PB exchange correlation. So this is intermolecular interaction curve for the fully MM models, which is the same as Xuecheng DFT results. So then we run the sDFT, normal sDFT QM with QM. We got the similar results. We know it will be good. So how about the QMM? So firstly, we only add the point charge to the density for the MM side. We don't think about any dipole. We only use the point charge density and we get still very good results. But the point charge is not updated. And this also not including the dipole. So we are trying to add the dipole also. So firstly, we directly take the dipole from the MM model results. And we frozen during the SF calculation, and we can get almost the same results as subsystem DFT, which is pretty good, but still not a real QMM calculation because we need to know the QMM results, the dipole, and we use it. So now we can use what we talked about. We use a fully self-consistent dipole here. So now we are run a fully self-consistent calculation, including update the dipole in the MM site, and we get a similar result as when we frozen the dipole from the MM model. So which is very exciting for us, and we think which is maybe is good or useful for when we push to large other systems. And when we look at entry contributions, so this, when we can see here, so the interaction energy, of course, is the biggest contribution to the total energy. But when two molecules become closer, the QM subsystem also give a very big energy contribution here. And for the interaction energy, yeah, electrostatic is also the biggest contribution. But still, when the two molecules become closer, the non-negative term also very important here. Yeah, that's the result we got now. And we haven't implemented the forces, so we are doing now, and we hope we can finish very soon. We can run some real dynamic results. And at last, I want to thank all the members in our research group. And I also want to thank Paseni research group because they help working on all the QM side. Yeah, thank you for your attention.
Thank you, Xuecheng. We still have some time for some questions. We are super on time, so the floor is open for questions. So if you have any question, you feel free to unmute yourself.
I have a question. So, Xuecheng, earlier you said that in the massively parallelized Python code, you don't have an IO node to save the global density. But how do you obtain it, or how do you? Well, you need to calculate it to run the calculation, right?
Yes. All the functional we run parallel. So each CPU only have a piece of the density and potential. And we through the parallel to run all the calculations. So anytime if the functional or the properties is dependent on the density, we have to run the parallel because there's no node or the CPU contain all the density. It's all the parallel and distributed. So that's why we can go to a very big system, because if we don't do that, we see all the data on the one CPU. As soon as you have a very big system, the memory will be crushed. You will auto memory.
Okay, so we have any other question? Okay, Anton. Yeah, Anton, go ahead.
Yeah, sorry to monopolize this discussion, but another question: when you choose the this Gaussian pseudodensity for the MM part, how do you choose the parameters, so the width of the Gaussian function?
Yeah, that's a good question. Now we just use, yeah, this parameter is very tricky here. In principle, we need to optimize and run a manual calculation, but now we just fix a number, make sure that the code can convert, because for the point chart, if you give 2 weights, it's not physical. So we have to give a smaller. So we just choose a sigma is smaller enough, but still not crush the potential. So it's a kind of optimized sigma here. Yeah.
Okay, thank you. So still we have time for one more question if someone has any other question. Yeah, Gabriel, if you have any question.
So, sorry, that was quite tentative. So I'm just wondering, given that you're putting these, you're dealing with these very small subsystems, I'm wondering how it deals with localized magnetization or spin states within a large periodic box.
Sorry, could you repeat your question again?
I'm just curious how this how the system deals with the localized spin states, or magnetization.
Okay, yeah. Because we are a density functional, we are still using DFT. So all of these will be handled based on the density functional. So we use a non-negative term to describe this interaction and all of these, all of these interaction between the subsystems.
Okay, thank you, Xuecheng. Thank you for the presentation.
Yes. Thank you.
So, please. Okay, thank you.